Science currently recognizes 8 distinct mechanisms of cellular death operating simultaneously inside the Alzheimer's brain. From cells rupturing under the weight of their own biological waste, to iron-driven lipid oxidation, to outright energetic starvation. This is what neurodegeneration actually looks like at the microscopic level, an intricate, highly organized biological circuit tearing itself apart into chaotic debris. For decades, researchers have treated these specific death mechanisms as competing hypotheses, arguing over whether the disease is primarily a protein clearance failure, an inflammatory crisis, or a metabolic collapse. But treating these as parallel, isolated events fails to capture how the brain actually deteriorates. The spectrum of collapse framework formalizes these chaotic mechanisms by mapping them onto a single measurable axis. This model plots every major vulnerable cell type across the established spatiotemporal progression of the disease, known as Braak stages. What emerges from this mapping is a specific trajectory, the catastrophic transition between two completely different types of cellular failure. To build this spectrum, we have to determine the exact placement of each death modality. The primary criterion is calculating the origin of the lethal signal relative to the dying cell. Does the threat come from inside the cell or from its environment? This diagram establishes our analytical scale. The 0 mark is the intrinsic pole. Cells die strictly from internal quality control failures over decades. Panthos plots perfectly at 0. The 1 mark is the extrinsic pole. Cells die rapidly due to an overwhelming chemical assault. Excitotoxicity plots exactly at 1. These poles require completely different pathological dynamics. The left side is a slow, silent internal erosion. The right side is a rapid, violent external assault. By tracking the origin and the speed of cell death, the intrinsic-extrinsic axis organizes a tangled web of isolated theories into precise spatial coordinates along a single timeline. The very first cells to accumulate pathology and die in Alzheimer's disease are the noradrenergic neurons of the locus coeruleus and the serotoninergic neurons of the dorsal raphe. These are two small, dense nuclei located deep in the pontine brainstem, well below the cerebral cortex. Their anatomical profile makes them extraordinarily vulnerable. They maintain massive, sprawling axonal projections that reach across the entire brain, and they fire continuously during wakefulness. This constant tonic firing creates an immense, lifelong metabolic burden. Looking at our timeline, the death of these cells falls firmly in phase 1. They map tightly between 0.0 and 0.2. Their death is purely intrinsic. Exhausting their internal energy reserves, they die through parthenoidos. No external inflammatory trigger is required. Despite this being the physical onset of neurodegeneration, losing up to half of these specific cells produces 0 detectable clinical symptoms in patients. The aminergic system masks the loss through aggressive structural redundancy. The surviving neurons simply sprout more branches and increase their firing rates to maintain normal neurotransmitter levels. But this biological compensation forces the survivors to work even harder, accelerating their own energetic burnout. For the first 20 to 30 years, this slow internal erosion is clinically indistinguishable from standard biological aging. The disease remains a slow, silent problem until it reaches phase 3. This is the inflection point where the cumulative internal damage actively forces the two poles of the axis to couple together. This axis now highlights the center of the spectrum, from 0.5 to 0.7. This is the coupling zone. After decades of processing dead neurons and accumulating toxic debris, the brain's immune cells, the microglia, hit a breaking point. They lose their ability to maintain local tissue health and shift into a post-homeostatic state. When microglia abandon their homeostatic role, they pump a potent mixture of cytokines and enzymes into the extracellular environment, saturating the surrounding space. This chemical release triggers the degradation of the perineuronal nets, or PNNs. These nets are specialized geometric structures that tightly encase the brain's fast-spiking parvalbumin-positive interneurons, acting as physical shields and chemical buffers. Once the microglial enzymes hit them, the protective mesh dissolves. The loss of the perineuronal net leaves these critical inhibitory neurons entirely naked to the extracellular environment. Stripped of their armor, they are immediately hit by a multimodal assault. Ambient glutamate overstimulates their parasympathetic receptors. Iron released from the decaying net drives severe lipid oxidation, known as ferroptosis. And the immune system itself targets their newly exposed synapses for phagocytic engulfment. This is a pure environmental execution. On the analytical spectrum, the vulnerability of PV-positive interneurons spikes at the far right, firmly occupying the 0.8 to 1.0 extrinsic pole. The transition from mild cognitive impairment to full dementia is a sudden mechanical crossing, moving from decades of slow inside-out cellular failure to rapid outside-in assault. The rapid elimination of PV-positive interneurons removes the primary inhibitory brake from the brain's cortical circuits. Without that braking mechanism, the entire network destabilizes and fires without restraint. The surrounding pyramidal neurons, which are responsible for memory, become violently hyperactive. They release a massive flood of excess glutamate, creating a toxic, overstimulated environment that damages neighboring cells. This intense external stimulation forces the pyramidal neurons to fire at rates they cannot sustain. The increased metabolic demand entirely depletes their already weakened autophagic and mitochondrial systems, triggering their internal collapse via panthos. The local circuit changes a cell's position on the vulnerability spectrum. The pyramidal neuron slides rapidly from a slow 0.2 intrinsic erosion right into the 0.7 zone, dying from a lethal combination of internal exhaustion and circuit-level hyperexcitability. By phase 4, the cascade has reached the neocortex. The brainstem aminergic nuclei, the interneurons, and the pyramidal networks are all collapsing simultaneously. Every single death modality on the axis is now active somewhere in the brain. Severe dementia is the biological manifestation of the entire spectrum of collapse firing at once, locked in an inescapable feedback loop. Mapping the axis reveals a critical distinction in the disease timeline. Intrinsic erosion is a feature of the aging brain, while the phase 3 crossing initiates the extrinsic network failure. This chart shows that because the cell death mechanisms change so drastically over time, therapeutic strategies must be mapped directly to phase-specific windows on the axis. During phase 1 and 2, interventions must focus strictly on internal quality control restoration. Supplying NAD+ precursors or mitochondrial support can structurally stabilize the cell's energetic baseline, but to prevent the downstream cascade, this therapy must begin decades before the first clinical symptom appears. If a patient reaches phase 3, the strategy must pivot entirely. You can no longer treat the internal erosion. You must execute an acute multimodal blockade. This means administering NMDA antagonists, ferroptosis inhibitors, and complement blockers before the interneuron population is depleted. To know which strategy to apply, clinicians need a definitive structural biomarker. The physical state of the perineuronal net indicates whether a patient is experiencing slow age-related decline or actively entering the rapid phase of neurodegeneration. Addressing the disease requires tracking these cellular coordinates and intercepting the moment the brain crosses the axis of collapse.